we will introduce the D3PO method, an approach that enhances image generation using human feedback. The paper is titled, Using Human Feedback to Fine-Tune Diffusion Models Without Any Reward Model. The main contributions are as follows. Firstly, our approach revolutionizes fine-tuning diffusion models within the LHF framework by bypassing resource-heavy reward model training and leveraging direct human feedback, enhancing efficiency and cost-effectiveness. Our work extends DPO theory into a multi-step in DP, demonstrating that updating the policy directly based on human preferences within an MDP is equivalent to learning the optimal reward model first. The effectiveness of our method is showcased through experiments, where human feedback effectively addresses hand and full body deformities, enhances image safety, and improves prompt image alignment. The common paradigm for fine-tuning large language model or diffusion model is our LHF, a two-step process. First, constructing a reward model from human feedback, and then use this reward model to fine-tuning the pre-trained model. However, training a robust reward model requires extensive data. Our aim is to fine-tune the model using datasets rather than necessitating the training of a high-quality reward model. The question at hand is, can human preference datasets be directly employed to fine-tune pre-trained diffusion models for enhancing image generation, bypassing the need to learn a reward model? To address this problem, we start by conceptualizing the denoising process within the diffusion model as a multi-step Markov decision process, MDP. We treat the noisy image, text, and the current denoising time t as states in reinforcement learning. The denosed image generated is regarded as actions. Other definitions are provided as follows. Here's a concrete example. S0 comprises the Gaussian noise xt, denoising time 0, and the text, a cute cat. After t denoising steps, the state transitions to street, where it includes the denosed clean image x0, denoising time t, and the same text, a cute cat. We aim for the images generated after denoising to be good. Therefore, the objective is to learn a denoising policy, which can maximize the return or cumulative reward of denoising. This optimization task is our L problem. To maximize the cumulative reward, the formal expression for the optimization objective of policy pi in state S can be written as maximize q asterisk, which denotes the optimal action value function. To address the out of distribution issue, we employ KL divergence to ensure that the fine-tuned policy does not deviate significantly from the pre-trained policy. By solving the optimization objective with KL divergence, we can derive the explicit relationship between Q and the optimal policy. Leveraging this formula, we establish the connection between the optimal Q function and the optimal policy. If we manage to establish the connection between human preference data and the optimal Q function, we can directly fine-tune the policy using this data, bypassing the need for the optimal Q function. Based on preference-based reinforcement learning theory, it is feasible within the MDP framework to learn an expression for the sum of rewards based on human preferences. We construct a relationship between Q and the sum of rewards, and demonstrate that the distribution learned through human preferences is approximately equal to using Q and the sum of rewards. Therefore, we can learn Q values through human feedback. Through the aforementioned series of equations, we derive a formula for directly fine-tuning diffusion models using human feedback. However, this formula only updates the probability values at time S0 and cannot update the probability values at other steps, resulting in low sample utilization. Additionally, as we cannot determine which step of the noise is better, we can only determine whether the final image wins or fails, which is akin to the comparison between final victory and failure in chess games. Drawing inspiration from methods in papers such as AlphaGo, we believe that in the denoising process, each step is good for good images, and each step is bad for bad images. Therefore, we can construct T additional subsequences to update the parameters. By utilizing these additional T subsequences, the probability values at each step of the denoising process are updated, leading to a T-fold increase in sample utilization. Here is the overview of our method. In experiments with quantitative metrics, preferences are established using existing reward models, or the relative magnitudes of specific quantitative metrics, as proxies for human feedback. A is deemed preferable if its reward, or objective surpasses that of B. We contrast our approach with DDPO, POC, and reward-weighted methods, which rely on accurate outputs from quantitative metrics or a reward model. Conversely, our method solely depends on relative magnitudes as preference relations, yielding results comparable to these methods. In the reduce image distortion experiment, we improved the fidelity of hand and person generation using human feedback. The left image shows the output generated by the pre-trained model, while the right image depicts the results after fine-tuning using the D3PO method. We conducted experiments on prompt image alignment, and the results before and after fine-tuning are shown in the figure. It can be observed that after fine-tuning, the images better match the description provided by the text. We compared our method with others, and based on human voting, evaluated the final results. It was found that our method obtained a higher number of votes, indicating that the generated images better corresponded to the provided text. Thanks for watching. Below are the links to our paper and code. For any inquiries, please feel free to contact the authors via the email provided below.